Hello there. Welcome to our today's science lesson. The topic for the day being physical and chemical changes. You realize that from our previous topics, we talked so much about elements and compounds, the names, the symbols of the elements, the compounds in terms of their names, in terms of their formula, and even how that name comes about to be the exact name for that particular compound. But what we didn't look at was how does that formula come about from maybe a particular element or particular elements or from other compounds. In our today's lesson, which is the topic to do with the physical and chemical changes, we want to look at some of those areas or how some of those compounds come to be the way they are, and later on see how even those properties we looked at when we were looking at the periodic table, that these are the properties that make these elements to be called metals or to be called nonmetals. Those properties are also going to be a very big integral part of our topic. Now, this topic is mainly going to talk about, we want to look at in general what the topic is going to talk about. You realize that this is relatively a wide area because it is like mainly talking about what chemistry as a science of as a part of science. Chemistry as a part of science talks about. Chemistry is just about reactions. Reactions and reactions and reactions. But in those reactions, they can be categorized into physical and chemical. All types of reactions can be categorized in terms of physical and chemical changes. So, we want to look at the kind of chemical reactions we have. How many or which type of chemical reactions do we have in our part of science called chemistry? We also want to look at what are the signs for you to tell me these are chemical reaction or these are physical reaction. What are the signs you are using to categorize, to group, to state that these are physical change or these are chemical change? So we want to look at the signs, and also we want to look at the patterns in chemistry. And here we want to look at the chemical patterns. Remember, when we were talking about the periodic table in our previous topic, we talked of a group or a family. Why did we call it a family or a group? We looked at the patterns on how those particular elements in that particular family or in that particular group are having or are reacting. For example, if you look at group 1, which we call alkali metals, they have a pattern on how they react. And this pattern is in relation to the electronic configuration, where we saw that the outermost orbit, what we also call the outermost energy level, has only one electron. So because of the one electron in lithium, starting from hydrogen, though it is found in both in group 1 and group 7, but starting from hydrogen, lithium, sodium, and so on, you find that they will have a particular chemical pattern in terms of reactions. So we also want to look at such a type of patterns. It is now not in terms of groups, but a pattern of reaction. If a particular type of reagent is used. So that in case you haven't even learned about that chemical or that particular compound or that particular element, but having known the pattern, you can easily predict the results of that particular reagent even if you have never used it, so long as you know which type of reagent it is. We shall also look at chemical properties of substances. Chemical properties of substances. You realize that on Earth, different substances are used for different purposes, uses. All of these uses are not just by coincidence. Something must have been done on that particular substance, and that is a study to discover, to find out, to get those properties of that particular substance. Let's take an example of a metal. Why should you choose a particular metal for a particular use? You will have picked out the properties the metal has that are suited, that are related, that are important when it comes to that particular use you want. Giving an example is aluminium. Aluminium is a very important element, which gives us a substance called aluminium metal. Is an element called aluminium, giving us a substance called aluminium metal. This aluminium metal, as a substance, which is a metal, has several uses. These uses do not come in just by accident. It is a study that has been made on this aluminium metal to discover that aluminium is strong, to discover that aluminium is light, to discover that aluminium is resistive to corrosion, that has made that aluminium to be used in various parts. For example, aluminium is used in making door frames, making window frames, making bodies like aeroplane bodies. Why? Because you first of all look at what are the activities that will be taking place around that part, like around the door. Probably it will be exposed to water. That window, probably it will be exposed to water. So you will want something that will resist water. Look at a plane. This is a body that will be exposed to various corrosive conditions, hardy conditions. So you will want something that is resistant to that type of corrosion. You will want something that is strong, because remember, the plane will be passing through areas that have different pressures. So you have to resist that variation in pressure. Remember, the plane must be strong but light. So you also have to look at the material should be light enough so that the plane is not excessively heavy, but it should be strong. So you find that aluminium comes in handy. A study must have been done to get those properties of that particular substance. And also, you have to also to look at other properties. For example, just to add on, a glass. Look at a glass. Why should a glass be used the way it is used? You can see through it. But it is strong enough to give the shape of that particular maybe structure you want. Look at a glass in front of that's the windscreen of a vehicle, of anything, or even that glass on a window that has a very big window pane, very big. Assuming you used a piece of transparent polythene paper, could it work very well like a glass? The answer is no. So you find that a glass will come in very handy because it is strong enough to give that shape, but in addition, your eye will see through it. Again, look at other factors, environmental factors that will be playing. Glass cannot be scratched. Remember that glass can be a glass on a window or a door where there's a small child who will be playing around with the door, with the sharp objects, scratching on that glass. It cannot be getting those marks. Look at a windscreen. Even if you go and scratch it with maybe a nail, it will not get that scratch. But assume it's a nylon paper, it will always get torn. So you find that because of such properties, being tough, being strong, transparent, plays in as a very important factor, and that is a property that has been used to choose on what is to be used where. And that is what we shall be looking at in this topic. Now, the other thing we need to realize before we proceed with this topic is we have to get an overview of some various aspects we covered in the previous topics. Remember, we are now talking about reactions. In our previous topics, we were not seriously talking about reactions. We were only mentioning. If it is a compound, we only mentioned a compound like sulfuric 6 acid or sulfuric acid, hydrochloric acid, sodium carbonate. We didn't talk about how that sodium carbonate was made or how that sodium carbonate can react. We only talked about sodium metal. We didn't talk about how that sodium metal reacts. We only say that when it is reacting, we look at the electronic configuration having one electron. Yes, but that was the end. For now, we have to go in details of it. We also saw so many other aspects like what is an element, what is a compound. Get the difference between the two. We got the difference, yes. But how that compound comes about, we don't know. And so many other areas. So I would like us to go through the various small areas of the previous topics using questions as we answer those questions to remind us of what we need to know in the present topic that is related to the previous topic. Remember, we have always to be safe. Safe in the sense that we are talking about changes. And changes here we are talking about reactions. And some reactions cannot be very comfortable to handle without knowledge. So with the knowledge, you will handle. But without knowledge, you can easily harm yourself, or you can easily get out getting something wrong from what you expected. So I will want us to go through some questions as we answer to remind ourselves and also to update ourselves on what we need to know about the present topic. So the first thing is, in this topic, we need to know how to write simple chemical equations for chemical reactions. Simple chemical equations for chemical reactions. In these simple chemical equations, remember, chemical symbols are important. We learned that in our previous topic. Chemical symbols, very important. Chemical symbols, we have chemical symbols for elements and chemical symbols for compounds. Though we didn't cover that as an equation or writing equations in the previous topic, but that equation has a component of a symbol, what we covered in our previous topic. We also need to look at or recall ourselves on safety issues, safety areas. In our previous topics, you remember we talked about things like kinetic theory of matter, where we saw that matter in a gas has more energy than matter in a liquid and solid. So you need to realize that when you will be having reagents combining that are in a gaseous state, you expect the reaction to be of high intensity than reagents that are in maybe in a liquid or in a solid, if they are of the same type of reagents. But if they are different, they can be even in a gaseous state and still you be able to manage. So you need to also understand that aspects in terms of the kinetic theory of matter, which is to do with the energy in the particles. We also need to look at how maybe to carry out the experiments. How do you carry out the experiments? Look at the periodic table. In the periodic table, when we were talking about the lanthanides and actinides, looking at most of those elements, and also looking at again the transition metals, elements, some of those, we saw that some of those elements are heavy, and because of that they are unstable. And being unstable, it means they will always undergo what we call decay, decomposition. As they decay, they release very powerful particles, energy, which without knowledge, that change can cause a problem. But with the knowledge, you will always feel happy because you will find solutions to various big problems. And I mentioned a problem of electricity, power. We require a lot of power to run our industries. We don't have enough. How would we do? How would we tackle that problem? We use such a series of reactions where the changes, those reactions will lead to a lot of energy being produced, which can be used comfortably in running industries. Again, we also have to look at things like what are reactants in a chemical change? What are reactants? Because remember, we are talking about reaction now. Whether it is physical or chemical, what is a reactant? Or what is a reagent? It's the same. A reactant or a reagent? A reactant or a reagent, these are substance or substances that are going to combine. These are substances that are going to combine to form a new other substance if it is a chemical change, a new other substance if it is a chemical change, or just combine to form a mixture, meaning that the two or the more reagents will still maintain their original characteristics, original properties, both physical and chemical, but they are together to form a mixture. So that gives a difference between a mixture and a compound. In a mixture, whatever you put together will still maintain their original chemical properties or physical properties, and both chemical, physical, or both chemical and physical, they will be maintained. But in a compound, that is in a chemical change, the product will be totally different from the reagents. So maybe let's have kind of a demonstration there. If I have this box plus, that box plus this one, we shall get, if I can use this to show that these are a compound, they are combined. So this is totally different from this one. But if I can have this, then plus this, and I get that. They are together, they are not together. But as much as they are together, each one of them is on its own. So these and these are still maintaining their original properties. These and these are still maintaining their original properties. This one is a mixture. But look at this. They are now combined. You cannot separate the two. So this one gives us a compound. This is a reagent. These are reagent. But this is a product, a compound. These are reagent. These are reagent or reactants. And these are product. Here we shall talk of physical change. But this one we shall talk of chemical change. The other question is, what do we call the substance formed by a chemical change? What do we call the substance formed by a chemical change? The substance formed. Yes, these are product, but we are talking about how do we call this compound? I've given the answer. How do you call this substance that you have a reagent plus another reagent, but you are talking about a chemical change or a chemical reaction? The answer is a compound. The answer to that is a compound. What is the other name for a chemical change? What is the other name for a chemical change? So you can either use chemical change or try to get it. We have physical and chemical. Do we have any other change? Any other name to stand in for chemical change? Yes, the name is permanent change. It's a permanent change. Permanent meaning that you cannot reverse. So I'm introducing here another word, reversion or reversing or reversible aspect of the reaction. So where you will have a process of reversing the product to reagents being so easy physically, we call it a physical change. But where you will find that reversing the product to reagents is not easy And if it is to be done is through a chemical change, then that is a chemical change, which is also a permanent change. It's the same, because you cannot reverse, I cannot now reverse this one to this, but I can easily reverse this to this. So this one is a permanent change, or you can also call it a chemical change. The other question is, what is chemical decomposition? What is chemical decomposition? These are things we shall be getting as we go on with our topic, chemical decomposition. Now there are two decompositions we shall really talk about, chemical decomposition and thermal decomposition. Chemical decomposition and thermal decomposition. Now the first one is chemical decomposition. When I have a compound like calcium carbonate, this is a compound. We talked about such a compounds in our previous topic. And I want to break it. I can do it in two ways. I can either add in something like an acid, or add in heat energy. When I add in an acid, for example, let's talk of addition of hydrochloric acid. I add hydrochloric acid to this calcium carbonate. If I add in hydrochloric acid to this calcium carbonate, you will find that this and this will react such that I will now have calcium chloride plus carbon dioxide plus water. What have I done to the calcium carbonate? I've decomposed it, then used the components that have come from the decomposition to react with the acid to give me other new compounds. You can see this calcium carbonate, but that is calcium chloride, totally different. We cannot get the calcium chloride if the carbonate unit was still there. So the first thing you did was to decompose this, to break it. Decomposition and breaking is the same. So the first thing was you break it, you decompose it. But what are you using to decompose? This is a chemical. So we call such a chemical decomposition. But I can still do it using heat energy. So if I can have now heat energy there on this, I will get a new product. And the new product here will be calcium oxide plus carbon dioxide. Looking at the products and the reagent, those are two different compounds. This is calcium carbonate and that's calcium oxide. This is calcium carbonate and that is carbon oxide or carbon dioxide. Carbon oxide, carbon dioxide, one and the same. So in the second aspect where heat is being used, we call it thermal. Thermal means temperature. Thermal decomposition. And where we have used an acid is called chemical decomposition. Now that is all about kind of new aspects of questions in relation to the topic. But the other questions, as we are going to look at them, they are arising from the previous topics. The ones we have just looked at are a little bit new, like thermal decomposition, chemical decomposition, how do we call a chemical, substance formed when a chemical reaction takes place, what is the name of a chemical change, the other name. Those are new terms, but we have gone through. Let's look at other questions. What is an element and what is a compound? What is an element and what is a compound? Those are things we talked about previously, but they are important in the present topic. That's why we need to revisit that. An element is the simplest part of any reactant we know. Now I'm changing the words a little bit because I have to suit the topic. So when you talk about an element, you are talking about the simplest reagent you are ever going to look at. Any element, any atom you will have is an element. An atom is an element, single, not a molecule, an element. But if that element will combine to have maybe two elements together, that's to form a molecule, that becomes a compound. If that element will combine with others to form another formula, it can be a radical, that's a compound. It can be any other compound, which is not a radical, neither is it a molecule, that's still a compound. So it is giving us the difference between a compound and an element. An element, for example, calcium, but a compound, for example, calcium oxide. So an element is the simplest particle that will be involved in that chemical reaction, simplest particle that will be involved in a reaction, and a compound is the product that will be formed in any chemical or permanent change you will have to encounter. Is any product that will be formed in any chemical or permanent change you will always be working on. Another question is, what is a chemical formula for water, sulfuric acid, hydrochloric acid, and nitric acid? Looking at that, these are very common reagents, and they are the very reagents we shall be handling in this topic of ours. So we have to remind ourselves on their formulas. You remember we talked about formulas and even the names. So here you have been given a name that uses this name in this reaction. And as I've said, in chemistry is about reactions. We have our own language of using symbols, not always just using words. So when you are writing that symbol, which symbol are you going to use for water? Which symbol for these common acids I've mentioned? So for water it is a capital letter H to capital letter O. For sulfuric acid, it is capital H, two of them, capital S, capital O, 4. For hydrochloric acid, we also have nitric acid. So for hydrochloric acid is capital H, capital C, small l. L is written just as 1, small l. Then nitric, we have capital H, capital N, capital O, 3. Now what are we seeing? We are seeing that in all these formulas, the first element is hydrogen. The first element is hydrogen. There is something we need to clear, that even if here we have hydrogen, 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 water is never taken to be acidic. These three are acids. This one is not acidic. So it's not always that when you see a hydrogen in a compound, then it qualifies the compound to be an acid. I chosen this so that we can clear on this. This is a neutral substance. Water is a neutral substance. If you are to test using the pH, you will find that the pH of water is 7. Not unless it has been contaminated. But if it is pure water, then it will have a pH of 7, showing that it is neutral. However, for sulfuric, hydrochloric, and nitric acids, they all also have these hydrogens, but now for them, they are acids. Now why? The reasons why these ones are acids are when you add to this water. You add water to all this, they undergo dissociation, what we call chemical decomposition. Now you can see the term we have just looked at is already coming in handy to understand this. It undergoes chemical, in this aspect, what is now a chemical? It undergoes chemical decomposition. And in the decomposition, it causes what we call ionization. You form ions. You form ions, and the ions here will be hydrogen ions coming from the acid and water. Then we also have these sulfate ions. Now, because of the hydrogen ions, which will also be for hydrochloric acid and nitric acid, because of the hydrogen ions, the solution now qualifies to be called an acid. So you can see decomposition there, chemical decomposition has now been applied or used. The other question is, what is the chemical name for table salt? So we look at chemical names. We talked about how to name chemical compounds in our previous topic. Table salt. That is a compound that I'm sure if you are given a nice meal but without that table salt, you will really curse that person, whoever prepared the food, because it will not be tasting well. So what is this good but very small? You know, very small. It looks insignificant but very important. Called table salt. The name to that is by formula sodium chloride, and the name is sodium chloride. Sodium chloride is sodium chloride. However, remember, we are being asked, what is the chemical name for table salt? Table salt. You need to realize that table salt as table salt is different from sodium chloride that will be found in a lab somewhere. Where does the difference comes in? In that table salt, if you have any package of a table salt, if you read on it, you may find that there are some other writings that are on top showing the ingredients in that crystal. So it is not just pure sodium chloride. And in fact, there are those ingredients, those additions that make it behave the way it does. Because you remember, if you open that, if you get a new packet of common table salt, new packet, not yet opened, if you move the packet, you may find that maybe the salt will be moving inside. But if you open it, leave it for some time, a day or two, you will find that now the particles moving, the crystals moving inside is a bit difficult because it is now wet. What made it to be wet? It is not just because it is sodium chloride. It is because it has another addition in it, and the addition is magnesium chloride. Magnesium chloride. Magnesium chloride. Now, as we shall be going on with our topic, we shall understand much more about this. Remember, I just mentioned that we shall be talking about chemical properties of substances. Chemical properties of substances. And this will be in relation to their use or not being used for a particular substance. So we shall see the properties of magnesium chloride that makes now, though in a small amount, that makes now the sodium chloride behave the way it does, and that's why we call it common table salt and not sodium chloride, because it doesn't have just one pure compound, it has two compounds. And in fact, some, they also add in iodine. They add in iodine, so you'll find that it is called iodized table salt. Iodized table salt to treat or to control things like goiter, the swelling of the neck. I'm sure maybe probably you have once seen somebody maybe swelling the neck here or some at this part. Most of the men are backside, and the ladies is usually the front part. That is called goiter and can be controlled with the addition of iodine in the common table salt. So you find that though this one is not main, The main one is magnesium chloride. Another question is, what is, so let's get the names of this. What is this? We also have this. Oh, sorry. It must always follow rules. And the rules is capital nitrogen, capital oxygen. I had used a small one, which is wrong. Then capital sulfur, capital oxygen, then 2. Let's get the names to this. These are things we did. This is oxygen, having 2 atoms of oxygen, so which means we can call it diatomic. This one is nitrogen, full name, first element, di, because there are 2. Which are these that are 2? Oxygen. Do you write the full name of the second element? No, you just pick part, which is ox. Then you fill in with the IDE, oxide. So, nitrogen dioxide. Same to this, sulfur dioxide. Those are the names to that. The other question is, what is a proton? What is a neutron? You remember when we were talking about the development of the periodic table and so many things to do with the scientists that are involved in chemistry. We really mentioned how that atom came into being and what are the inclusions in an atom. And we saw that in an atom there are 3 subatomic particles, and that is a proton, a neutron, and an electron. We even went further to look at who did what and when. And the most recent was a neutron, which was done by Jatwick, which really changed so many things in terms of how even the periodic table was now worked on. Mendeleev started on it and had some problems because of some elements kind of looking the same, but they are different. He didn't have how to tackle the problem, but when Chadwick came in with the neutron aspect, then some air was clarified. So, what is a proton and what is a neutron? So, these are subatomic particles that are found in an atom, and not just in an atom, but in the nucleus of an atom. Protons and neutrons are subatomic particles that are found in the nucleus of an atom, and in addition, these are the subatomic particles that are responsible for mass of an atom. If you say mass of sodium is, if I can follow the format of the periodic table we had the atomic number up here and the mass number down. So if we can say the mass is 23 and the atomic number is 11. What is this 23? This 23 is equal to the number of protons and the number of neutrons in this sodium, telling us that if protons, because atomic number is the same as number of protons, if protons are 11, that is protons are 11, then automatically neutrons will be 12, so that when you total, you now get 23. So protons and neutrons are subatomic particles found in the nucleus of an atom that are responsible for the mass of the atom. Responsible for the mass of the atom. The electrons are just found around the nucleus and in energy levels or in orbits. But those orbits have energies, so that's why we also use energy levels. The other question is, which element has the simplest atom in its atomic symbol? Which element has the simplest atom, and we also get its atomic symbol? So in anything, there is always a starting point. So with these so many elements we learned about, the naturally occurring 92 elements, though there are more than that, but the ones you can get at any single moment, 92 elements. Out of these 92, or all of them, the 118. Out of these 118, which one is the simplest? And what is the chemical symbol for the same? And the simplest should be the one that is called number 1, meaning that it only has one proton. Because we have from 1 to 118, including those that occur for a very short period, or naturally it is 1 to 92, whichever the number you'll be using, but you have begun from number 1. Who is this number 1? And number 1 means it's atomic number 1. And being that it's atomic number 1, then it means it has one proton. Which element is this? And the element that has one proton must be having one electron. One proton means one electron. So we are talking about an element that has an electronic configuration of just 1. And if it has an electronic configuration of just 1, then it means how many energy levels does it have, or orbits? It only has one orbit. One orbit. Then how many electrons does it have in the outermost orbit? 1. What we also call outermost energy level. So looking at how you constructed your periodic table, we said that you can have those periods and you can have groups. So this element that has one orbit, you check on 1. And 1 electron in the energy level, you check on the first one. So it will be the very first element that is placed at that particular point of our block periodic table. The very first point in this block periodic table. If you check in your periodic table, that element is hydrogen. And I've already even given the symbol of hydrogen. It is written that way. That is the atomic symbol. But we also need to know its chemical formula. There's a difference between symbol and chemical formula. So the symbol for this element I've just been describing is capital letter H. That is hydrogen. But as a chemical formula means how it is normally used as a reagent, as a chemical in any of these reactions, whether it is physical or chemical, but how it is used. Is it used as capital letter H? No, because it does not occur naturally as capital letter H. It does not occur monoatomically. That's what it means. Does not occur monoatomically, but it occurs diatomically. So we need to have two of them coming together so that we can now have diatomic hydrogen. And that is the formula of the chemical formula of hydrogen. Diatomic, because that is how naturally it is found. Then the other question is, what is the atomic symbol for potassium and lead? These I've only picked out two metals, potassium and lead. What is the symbol for that? Atomic symbol for that? Potassium, and we also have lead. Now, why I picked on these, there are those metals you'll find that the symbol and the name are a bit close by the starting letter, but some do not have any kind of relation. And this is, for example, potassium, which has a capital letter K, and lead is capital letter P, small letter B. That is the symbol for the two, potassium and lead. Where do we get this? You find that they are the scientists that came up with this used a particular name to describe this potassium. Like now potassium, it was kalium. Potassium was described as or called kalium. So because of that, the symbol K came from the name kalium to mean potassium. Lead was plumbate. Plumbate was the original name they used to describe lead. So the name, the formula Pb came from plumbate, meaning lead. After having looked at the questions we have just looked at, as I mentioned, the questions came from mainly the topics we had already looked at. These other questions we want to look at may borrow part of what we did in the previous topics, but some may appear a bit new. New or not new, we need to know the knowledge before we proceed with our new topic. So the question is, what is a precipitate? What is a precipitate? This is a term maybe probably you have heard of it, and these are the things we are going to be making as products in our chemical reactions, because that one can only be formed in a chemical reaction. So before we look at that chemical reaction and we encounter an example of a precipitate, we need to know what is a precipitate. So a precipitate is something in relation to solubility. Solubility. And in solubility here we are talking about a solvent which is commonly water. With the solubility you talk about a solvent, and the common solvent we talk about is water. Water which is a polar solvent. Polar meaning it has positive and negative in it. All solvents that are polar, it means they have part positive and partly negative. They are polarized. But we also have those solvents that do not have the polarization in them. So they are called nonpolar solvents. So you'll find that there are those substances that will dissolve in polar solvents but will fail to dissolve in nonpolar, and those that will dissolve in nonpolar and fail to dissolve in polar. Those properties will be discussed as we go on with the topic. But now, when you talk about a precipitate, you are talking about solubility of that particular substance. Solubility of that particular substance in water. Let's give an example as we go on to elaborate that. If I have a substance like lead sulfate, I'm using lead because we have just talked about it. Lead sulfate. Looking at lead sulfate as a compound. It is having 3 different elements in it, so that's a compound. You cannot break this one physically, so that's a compound. If it were a mixture, you could reverse it, but you cannot reverse it. So this is a compound. So this substance, if you are forming it in a reaction, and in addition to it, there is formation of water, or in that container where it is being formed, there is water as a solution, then this substance will be seen as a solid. Settling at the bottom of the container. Why is it settling at the bottom of the container? Because this substance, lead sulfate, will not be dissolved by the water. In so doing, then you will say the lead sulfate is now a precipitate. It will be said to be a precipitate. It has been gotten out of the solution. Now, to clarify this further, you need to know that for you to form a precipitate, you must come from a solution. For you to form a precipitate, you must come from a solution. So, two solutions can be colored or non-colored. That is colorless, like water. They can all look like water, but once you mix them as reagents, then something else happens. So we have a solution plus another solution or solutions. Then out of these solutions, whether colored or not, then you find a solid. This solid is what we call a precipitate, which will have refused to dissolve in water. And where are we getting this water? The water that is in this solution and the water that is in this solution will be unable to dissolve this compound. And an example here is like lead sulfate. You can have sulfuric acid plus something like lead nitrate. This one is a soluble compound. It will just be a clear solution like water. This lead nitrate. Sulfuric 6 acid will also be as clear as water. In fact, if you are not told and you are feeling thirsty, you can easily take these compounds. And that's why in the lab, there are rules. I said here that we should always also look at recalling safety issues. Safety issues, some of them are one, like all chemicals in a lab must be labeled. Because if they are not labeled, you find it in a cup and maybe it is sulfuric 6 acid or it is a lead nitrate. You will comfortably take it assuming it is water. So as clear as they are, immediately you add these two, you will find a white solid being formed. The white solid will be lead has combined with the sulfate part to form lead sulfate, which is insoluble, a white solid. That will be a precipitate. Another question is, what does PPT tell us? I've already explained that. PPT or precipitate tell us that the compound or the substance that has been formed is insoluble. Once you see a precipitate, anywhere, once you see a precipitate, then it only tells you one thing, that whatever you have formed is insoluble. If it were soluble, then you will not be able to see the solid, which you are calling a precipitate. But since you have seen that solid, then it means that substance is insoluble. So it is important to check on solubility of substances. Then the last quarter of the last part of these questions are still talking about some parts previously and some new. What do we call the distinguishing properties, the distinguishing characteristics of substances we use? How do we call, or what do we call the distinguishing characteristics of substances we use? I had already alluded to the answer. The answer is properties. Those characteristics that you will always use to distinguish between substance A from substance B, so that you can use those distinguishing characteristics to say, I'm now going to use A for this purpose and B will be used for the other purpose. Those are characteristics. We have what we call chemical characteristics. They will always be applied when you are choosing a property. An example is, why should I use sulfuric acid as battery acid? Why should I use sulfuric acid as battery acid and not hydrochloric acid and not nitric acid? And yet they are all acids. That goes down to properties of this acid that is different from the properties of these those other acids. So all those things, in one way or another, we shall be looking at them in the topic or in other topics to come, but they all go down to properties of that particular substance. Another question is, what is a distinguishing property of all metals? What is this distinguishing property of all metals? What is it that you use to say these are metals and these are not metals? The main distinguishing property, it is to do with the conductivity. all metals conduct an electric current. All metals conduct an electric current. And maybe just to clarify on that part, why metals, to clarify on the part why metals are conductors of electric current, is in terms of structure, whereby when you have a metal, pick any metal, may I use sodium? Sodium will have sodium metals packed together, will have sodium atoms packed together, and each sodium atom has 281 as electronic configuration. Because of having one electron, and yet it wants to have 8 in the outermost so that it is stable. We said that if the outermost energy level or orbit is full, then that atom will be stable, like the noble gases. So it will want to have 8, but it has 1. So it will have to weigh between, do I lose 1 so that I have 2, 8, I will still be having 8, or I gain 7 so that I can have now 2, 8, 8. You'll find that the first one will be much easier, losing 1. This 1 electron that has been lost, where will it be going to? It has nowhere to go. The 1 electron will be having nowhere to go. So it will just be found around the atom, which is now an ion, sodium ion, because it has lost the electron, so it becomes positive. But these electrons are allowed, they are mobile, they can move around. So we say the electrons are delocalized. The electrons are delocalized. So being delocalized, they can move from one part to another part. As they move, that is what we call current. Movement of electrons is what we call current. So that makes the metal to be able to conduct an electric current. So all metals conduct an electric current. The only thing that varies is the level of conductivity. Aluminium will conduct much better than sodium, because for aluminium it will give out 3 per atom. 3 per atom. But for sodium, we have only seen 1. So work done by 2 will be more than 1. And work done by 3 will be more than 2 and will also be more than 1. So aluminium is better, followed by magnesium, then lastly sodium, if I'm to choose only those 3. The other questions are, what decides which metal we use for a particular purpose? What decides which metal to be used for a particular purpose? Steel properties. 1. How strong is that metal? It goes back to this. How many electrons it is giving out. The more electrons you give out as a delocalized electron, the more stronger the metal is. That's why aluminium is stronger than magnesium, and magnesium is stronger than sodium. Because sodium only gave out 1, magnesium 2, aluminium 3. So aluminium becomes stronger and sodium becomes softer. You can even cut it using a knife. So you look at strength of the metal, look at conductivity. Maybe you want to use it as a conductor. Look at conductivity. Look at how easy you can shape that metal. Look at how you can mix it with another metal to form an alloy. Not all metals are the same. Then, why aluminium is used for door and window frames? It's still talking about properties. Still talking about properties. Why aluminium can be used for making window panes, window frames, door frames, and in addition, I even mentioned the aeroplane. Why is it used to make that body of an aeroplane? It still goes back to 1, the strength. Aluminium is strong. In also aspect of shaping it, you can shape aluminium very comfortably to different shapes, rods or sheets. And more importantly, for this aluminium is a reactive metal. So it easily reacts with oxygen to form aluminium oxide. To form aluminium oxide. You remember how these 2 and 3 comes in? 2 is the valence of oxygen and 3 is the valency or the combining power of aluminium. So it forms this aluminium oxide which covers the surface of aluminium metal, protecting it from corrosion from the environment. So you'll find that a new aluminium metal will look a bit shiny, but with the time it will start darkening a little bit, but no corrosion. It's just because of the formation of aluminium oxide, which is important in protecting the inner aluminium metal, and it stays for a much longer time. And lastly, what property of glass makes it very useful? I began with those 2 questions. Aluminium is transparent. Glass is transparent. Aluminium, as strong as it is, you can also take it to glass. Glass is also strong. You cannot scratch glass. That's why you can only use diamond to cut glass. You cannot use another thing because it is strong, it is tough. You cannot scratch it, favoring the use. If you use glass as a windscreen and it can allow scratches within a short period, you will find that that windscreen will not serving you well. If it were not transparent, how would you see then through the glass? So you find that the properties of it being transparent, being rigid enough to resist scratches, and being rigid enough to take a particular shape. Once it is shaped in a particular manner, it remains that way. It makes it very useful or handy in being used the way it is used. So in our today's lesson, we have been looking at, in general, the important terms, important aspects we need to understand before we continue with our new topic of chemical and physical changes. That marks the end of our lesson today. Thank you.